Welcome back to my class in problem solving, mathematical investigation, and modeling. In the last lesson, we took up step 2, which is designing a solution plan. Today, we will complete the steps in Polya's problem solving technique with step 3 and step 4. And step 3 is implementing a solution plan. And these are the steps for implementing a solution plan. Number 1, solve the problem using your plan. Number 2, be sure to double check each step. Number 3, if the plan is not working after a few attempts, try a different plan. 4. Allow for mistakes. And 5. Check your answer. The plan you designed in step 2 may not be the final plan because it may not lead to the solution of the problem, and you should remember that the plan may need some revisions. So what you do is you experiment with different solution plans and always allow for mistakes or errors. It is also suggested that you work collaboratively when you implement a plan. The last step in the fourth step problem solving method by Polya is reflecting on the problem. After students have completed their problem and they come up with a solution they are satisfied with, they should reflect on the problem solving process. Because by reflecting on the problem, by reflecting on the plan and the process of problem solving, much can be gained by looking back at what they have done, what they have worked, and what didn't work. And doing this will enable the students to predict what strategy to use to solve problems in the future. Some of the questions that you may ask your students to answer, and students should work within their collaborative group to answer and reflect on the answers to these questions. And you may ask your students to write their reflections in a mathematics journal, possibly an electronic version or completed on activity cards. And some of these questions are: number 1, can you check the result? Can you check the argument? Does your answer make sense? Did you answer all parts of the question? What methods work? What methods failed? What did you learn from completing this problem? Could I have solved this problem another way? Was there an easier way to solve this problem? If I encountered a similar problem in the future, how could I better solve it? What does mathematics really consist of? Well, some would say mathematics consists of axioms, theorems, definitions, formulas, and methods. Mathematics could surely not exist without these ingredients because they are all essential. But none of them is at the heart of mathematics. And mathematics really consists of what mathematics really consists of is problems and solutions. And mathematicians' main reason for existence is to solve problems. Before we define a mathematics problem or mathematical problem, we differentiate between mathematical question and mathematical exercise. A mathematical question is a task that can be assigned to a student, and the student is expected to carry it out. And at some later stage or time, the student is expected to submit an account of their answer. Thus, a mathematical question is a very broad, generic term used in all kinds of assessment. On the other hand, a mathematical exercise is a question whose solution involves only routine procedures. Having learned the relevant techniques, a student will be able to follow an obvious strategy and systematically apply the techniques in sequence of steps to reach a correct solution. This is an example of an exercise, and the instruction to the students is to calculate the definite integral of sine 2x dx to be evaluated from negative pi to pi. To answer this question, students need to know the indefinite integral of sine nx. In this particular example, it's 2x. And the value of cosine x at negative 2 pi and at positive 2 pi. For students who know how to apply this knowledge, the question is an exercise. Alternatively, students who recognize that sine is an odd function and know how to cancel positive and negative areas can solve the question without integration. For these students, too, it is an exercise. A mathematical problem is a question that is not an exercise. To put it in another way, a mathematical problem is a question whose process for answering the problem is unclear. But you should take note that it is difficult to classify a question on its own as a problem or exercise because it all depends on the student. A question for one student can be an exercise, while the same question can be a problem for another student. Thus, this definition of mathematical problem provides an immediate practical difficulty because, as I said, one person's problem can be another person's exercise. An example would be a question that is simply an exercise for the teacher, but that same question can be a problem for the students. However, there are defining characteristics of problems. And if you see these characteristics, then that problem is a mathematical problem. Novelty is one defining characteristic of problems. And in response to this novelty, the students requires creativity to solve the problem. And how can we see novelty in a mathematical problem? In a mathematical problem, novelty can be seen in the way the problem is formulated or is stated. And a mathematical problem that is novel requires a kind of strategy, creativity. It requires creativity to solve the problem. And novelty in a mathematical problem can be seen in the concepts that the problem addresses. This is an example of a mathematical problem. The problem presents a question from geometry, and for many undergraduate students, this question will be a problem, and very few will easily relate this question to some previously encountered ideas or procedures. And so they cannot immediately think of how to go about answering this problem. To them, this problem is novel. This problem, K, is a point on a circle sitting inside and touching a stationary circle of twice diameter. And the question is for the students to describe the path of point K as the smaller circle rolls around the larger one without sliding. In solving this particular mathematical problem, a relatively small deviation from the normal may be all that is needed to make or to solve this novel problem. Clarity in how to proceed depends on the student's perception and recognition. This is another example of a mathematical problem. It is a famous question because, in spite of its apparent straightforwardness, it poses real difficulties to many students. The problem says write an equation to express the statement there are 6 times as many students as professors at this university. Use S for the number of students and P for the number of professors. This problem was initially studied by Clement et al. In 1981, who posed the question to 150 calculus students, and 37% of them answered this question, this problem, incorrectly or wrongly. And two-thirds of those with incorrect answers were have the answer 6s equals b. In 1988, Fisher and in 1993, Stacy and McGregor revisited this problem, and students continue to perform poorly when attempting this problem. In this instance, the problem's novelty comes from requiring students to translate the words into mathematics. And this particular example of mathematical problem is taken as a problem of interpretation. This is another example of mathematical problem. It's called Goldbach's conjecture. And the problem says every even integer greater than 2 can be expressed as the sum of two primes. This statement of Goldbach's conjecture can be understood by students at secondary school, yet it has remained open for over 2.5 centuries. With this problem, the novelty is one of strategy. Where can one begin? What constitutes a solution? What arguments can be brought to bear? While it would clearly be unreasonable to expect undergraduate students to solve this, they can certainly be expected to attempt to solve this particular problem. This is another example of mathematical problem wherein the novelty can be found in the strategy that is to be used to solve this problem. This particular problem is taken from Durham University in one of the modules on problem solving. For a typical beginning undergraduate student, the statement of the problem is very likely to be clear, and yet a way to approach it and the form of an acceptable solution are not very clear. And the problem says which numbers can be written as the difference of two perfect squares. For example, square of 6 minus square of 2 equals 32. As I mentioned earlier, another way to bring novelty to a question so that it becomes a mathematical problem is to introduce new concepts or to redefine old concepts. And this is an example of a mathematical problem where the operation multiplication on the set of real numbers is given a new definition. We read, let the set R defined as the set of real numbers that can be divided by C for some C element of R is combined with the multiplication operation defined by. This is the new definition of multiplication of two real numbers x and y. And the student is asked to verify that RC, the real numbers that are divisible by C, is a group under this operation. Also, the students are asked to find the identity and inverse elements. For a student who has not taken abstract algebra, this question is likely to present an algebraic challenge because it is easy for that student to confuse the two types of product, the product obtained by ordinary multiplication of real numbers and the product of x and y obtained by this multiplication, binary operation multiplication defined by this x dot y equals product of quantity x minus c and quantity y minus c plus c. A student who has a knowledge of group theory or group will probably find this as a routine exercise to prove associativity and the existence of an identity and inverse elements, which are the three properties of a group. Word problems, which include algebra story problems, are questions presented to students in rhetorical form. And the first task of the student is to translate the text into more formal mathematics. And Polya asserts that word problems deserve a special place on the mathematical curriculum. For George Polya, the most important single task of mathematical instruction is to teach the setting up of equations to solve word problems. In solving a word problem, the student translates a real situation into mathematical terms. And in doing so, he has the opportunity to experience that mathematical concepts may be related to realities. Translating words into mathematics is still an important skill. When modeling a real world situation, we also need to represent it mathematically. We then operate on the resulting mathematical abstractions, but periodically check for a meaningful correspondence between the real situation and symbolic abstraction. Unlike problem solving, when modeling, we are very often required to make approximations to enable the resulting equations to be solved. A good problem and a good modeling question both require decisions on the part of the solver. This is all part of open close quotation making sense. Modeling is closely related to problem solving, and engineering and science, particularly physics, make use of mathematics in this way. It has been argued that word problems form the start of modeling. Many evidence have shown that word problems are initially likely to be problematic for many students until significant practice has been undertaken. Thus, these ultimately may become exercises. The word problems may ultimately become exercises and not genuine problems in the way that we have just defined what a mathematical problem is. However, many of the students find particularly these problems particularly difficult, and they are often encountered as problem solving tasks. It will be useful to distinguish a subclass of problems, and these are puzzles. Puzzles are subclass of problems. A puzzle is a particular type of problem that usually requires little prior mathematical knowledge. A mathematical puzzle need not have wider impact on mathematical knowledge or be a part of a circle of ideas. Puzzle can be happily self-contained. This is an example of a puzzle. It's called Bee and Trains. Two model trains are traveling toward each other on the same track, each at a speed of 5 kilometers per hour along the track. When they are 50 meters apart, a bee sets off at 10 kilometers per hour from the front of one train heading toward the other. If the bee reverses its direction every time it meets one of the trains, how far will it have traveled before it must fly upwards to avoid a grisly demise? It is tempting to dismiss puzzles for being educationally lightweight, but puzzles are can be valuable in a variety of ways. They can stimulate students' interest and provoke curiosity without requiring special preparation or background knowledge in mathematics. Puzzles can also suggest methods that can be useful in other contexts, and puzzles can give students a sense of achievement, even aesthetic pleasure, when they find a satisfying solution. These are the attributes or the criteria that may be used to determine if a problem represents an educational puzzle. Puzzles have the property of generality, simplicity, freestanding, being lightweight, and ingenuity. Generality refers to explaining some universal mathematical problem solving principle. This means that puzzles may require the solver to apply some mathematical problem solving technique. Simplicity, it has an entertainment value. It has a eureka factor, which means that a person who is able to solve the puzzle experiences delight and joy and satisfaction for having solved the puzzle. It is freestanding. Many puzzles require little or no prior knowledge of mathematics. Lightweight puzzles lack gravitas and without ramifications. Puzzles are made simple enough to be attractive for problem solvers. Ingenuity, it takes originality and creativity to solve a puzzle. This is another example of a mathematical puzzle, and this example illustrates the value of extending a diagram by adding extra information. And the trick here is to draw a third diagonal to produce an equilateral triangle. And the puzzle reads, two line segments are drawn as diagonals on the sides of a cube so that they meet at a vertex of the cube. What is the angle between the segments? Mathematics is a systematic way of structuring thought and arguments. And these two are tied closely to a coherent body of associated knowledge. Mathematical practice is concerned with finding solutions to problems, whether related to practical problems, which is the concern of applied mathematics, or internal to mathematics, referring to pure mathematics. In undertaking problem solving, a student needs to develop both intellectual and temperamental qualities. And these are some of the intellectual qualities that students need to develop. Students need to identify essential steps and work out a strategy. Students need to seek out relevant knowledge and use it or apply it to the problem at hand. Students need to use structured and logical arguments. Students need to carry through a plan accurately using a sequence of linked, that is related steps. Students need to know when to turn back in a dead end and try a different tack. Because as we said earlier, a plan may not work, and so the students have to make allowance for errors and mistakes in order to revise the initial plan. Students need to organize, present, and defend their solution. Students need to submit a solution to the scrutiny of the teacher or their peers. That is for the teachers and their peers to examine and study their solution. And students need to explore the consequences of their solution, ask further questions, experiment with hypotheses and conclusions, and try out generalizations. Some temperamental qualities needed for problem solving require students to: number one, accept the challenge and take responsibility for finding a solution. Problem solving requires students to be tenacious, that is, to be firm and strong. Problem solving requires students to be prepared to take risks, to tolerate frustration, to look back at their own work in a critical way, and accept criticism from others. By solving problems, students learn to apply their mathematical skills in new ways. They develop a deeper understanding of mathematical ideas, and they get a taste of the experience of being a mathematician. With success comes a sense of achievement, even enjoyment, and possibly an appetite for more. Repeated practice under these circumstances increases students' confidence for problem solving, builds up their stamina, and rewards perseverance. And by the process of regularly doing reflection on their problem solving activities, students can store up these experiences for future use. That completes our lesson for today in problem solving, mathematical investigation, and modeling. Thank you for joining me in my class today. And if you have questions, you ask your questions in the comments below.